We will now consider another type of load, and that is the linearly increasing vertical loading on an infinite strip. First, we take a look at the figure, and we observe that the load is linearly increasing. So from the zero magnitude up to an increasing magnitude. And then the strip is infinite. So we see here point A, and we want to know the stress increase, the vertical stress increase as an effect of this particular or this certain load. So the load is a linearly increasing vertical loading. So to know the vertical stress at this certain point as an effect of this type of loading, that is Q divided by 2 pi multiplied by the quantity 2x divided by b multiplied by alpha minus sine of 2 delta. So let us define the parameters. Q is the load per unit area. X is the horizontal distance of A measured from the minimum magnitude of the triangularly or the uniformly increasing vertical load. So this is our X. Next parameter is Z. This is the vertical distance of A measured from the ground level or the reference line. So this is our Z. Next parameter is the angle alpha, and alpha is the angle formed when lines from the minimum and the maximum magnitude are connected to the point of consideration. So this is our point of consideration. This is the minimum magnitude. This is maximum magnitude. So when lines are connected from the minimum and the maximum magnitude and connected to the point of consideration, there is an angle that is formed, and that is angle alpha. So note that this angle should be converted into radians. The value of alpha is always positive. Next parameter is delta. So angle delta is measured from the global vertical axis. That is our global vertical axis. And it is positive if it is counterclockwise, considering the orientation presented in this figure. So if it is counterclockwise, it is positive. Now, what if the loading has a different orientation? So let us consider the different behavior of angle delta with the different locations of point A. So first, yes, we have here your linearly increasing vertical load. So the angle delta is measured from the vertical axis up to the line connecting the point of consideration and the point of the maximum magnitude of the load. So in the angle delta, the angle is always measured from the vertical line. So since the direction is counterclockwise, delta is positive. What if the point is located somewhere here? If we are getting vertical stress at this particular point, of course, there is no angle that is formed. Therefore, the value of delta is 0. If the point A is somewhere in the midpoint or somewhere in between the loads, again, delta is measured from the vertical axis up to the line that is connecting the point of consideration and the maximum magnitude. So from here, we observe that the direction of the measurement from the vertical axis is clockwise. Therefore, the value for delta is negative. So same if the point of consideration is outside in this area, we put an imaginary vertical line load, and we see that the direction of the angle is clockwise. Therefore, our angle delta is negative. If the direction of the load is in inverse direction from the maximum magnitude down to the least magnitude, and our point of consideration is somewhere here, the signs of the angle delta from here will also be inversed. So on this side, our counterclockwise direction is positive, but on this inverse loading, the clockwise direction now becomes the positive. If we are considering the point A2, there is no angle that is formed, so that is 0. And then if the point is in between the load, counterclockwise direction now becomes negative, same as here. counterclockwise direction becomes now negative. So this is the variation of the sign of angle delta. Next is determining the vertical stress increase using method 2 or using the aid of a table. So again, the first step is to determine the value of 2z divided by b and 2x divided by b. So in determining the value of x, we have to consider the orientation based on the diagram. The strip load is located at first quadrant always, and x is either positive or negative based on its location from the origin as shown in the following figure. So we have here your strip load, which is always located at first quadrant. So this is our point of origin, and now the horizontal distance or the x distance, if it is going towards this direction, it is positive, and if it is going towards the opposite direction, it is negative. Take note this important concept in getting the value of 2x divided by b. And then after determining the values, we can now refer to table 3.5 for us to identify the value of c. And then from there, we can substitute it with the equation. And we can get or we can arrive at the value of the vertical stress increase. Let's take a look into this example. Refer to the figure 3.19 for a linearly increasing vertical loading on an infinite strip. Given that B is 3 meters, Q is 100 kilonewton per meter squared, determine the vertical stress increase at point A, and A has a coordinate of 6 meters and 1.5 meters. So 6 meters is the horizontal distance, 1.5 meter is the vertical distance. So again, we have here a linearly increasing vertical loading. The B is given, the width is given to be 3 meters. The Q is 100 kilopascal. And then we want to know the effect of this loading at a certain point that is 1.5 meters below the ground surface and 6 meters from the minimum magnitude of the loading. So first, we use the method 1, which is using the equation vertical stress at point A is equal to Q divided by 2 pi multiplied by the quantity 2x divided by B multiplied by the angle alpha minus sine 2 delta. So we know the value of Q to be 100 kilopascal. We know the value of X, that is 6 meters. We also know the value of B, that is given to be 3 meters. So let us identify the value of the angle alpha and the angle delta. So first, to determine the value of alpha, we said that alpha is the angle that is formed when we connect the point of consideration to the minimum magnitude and to the maximum magnitude of the loading. This is now our angle alpha. And then for our angle delta is measured from an imaginary vertical axis towards the line that is connecting the point of consideration and the maximum magnitude of the loading. So this is now our angle delta. So let us determine angles delta and angles alpha. To determine angle alpha, we will be considering this triangle. We can solve the value of angle delta by applying our trigonometric properties. We know that this dimension is 1.5, and we can also solve the value of this dimension since from this point up to this point is 6 meters and the width is 3 meters. Therefore, this is 3 meters. From there, tangent delta is equal to the opposite side over the adjacent side, 3 meters divided by 1.5 meters. Delta is positive 63.43. It is positive because the direction is counterclockwise. For the value of angle alpha, we will now be considering this triangle. Same trigonometric properties. We'll be using tangent, that is a tangent of this angle. And since we know the measurement of this side and the measurement of this side, that simply becomes tangent of the angles delta plus alpha is equal to the whole side, that is 6 meters, divided by adjacent side, which is 1.5 meters. This now becomes alpha plus delta is equal to 75.96 degrees. We know the value of delta. Therefore, alpha is 12.53 degrees. From there, we can now substitute the equation. Q is 100 divided by 2 pi multiplied by the quantity 2 times 6, our x, divided by the width, which is 3 meters, times the angle alpha, which is 12.53 degrees. However, we have said that we always convert the angle alpha into radians. So that is multiplied by pi divided by 180 degrees to convert it into radians. Minus sine twice the angle delta. Our value now for the vertical stress increase at A is 1.88 kilopascal. This is now our answer. We will be solving the same problem using table 3.5. So the first step again is to determine the value of 2z and b and 2x and b. From our figure, this is our loading and this is our point of consideration. The x is, the value of x is going to this direction, to the right. Therefore, the value of x is positive 6 meters. So always check the sign of x. Again, if the point of consideration is somewhere here, therefore, the value of x becomes negative because it goes to the opposite direction. We now substitute 2x divided by b. So 2 times 6 divided by the width, which is 3 meters. This is 4. And then the value of 2z divided by b, that is 2 times 1.5 divided by 3 meters, that is 1. After knowing the respective values, we may now refer to table 3.5 for us to identify the value of c. From the table, our value of 2x divided by b is 4. That is somewhere here. And then our value for 2z divided by b is 1. So we know that the value of c is 0.119. We now substitute the value of c to the equation. That becomes vertical stress is equal to c multiplied by the load, 0.0119 times 100. This is 1.19 kilopascal. This is now our answer. If we are going to compare it to the value we had solved a while back, that is 118 kilopascal, we can see that they are almost equal or the same.